Hello, everyone. At this point, it is expected that you have mastered the concept of kinematic quantities such as position, time, displacement, distance, speed, velocity and acceleration. In this lesson, we will learn an important type of motion in which the velocity of a body is changing at constant rate. This motion is called uniformly accelerated motion. Uniformly accelerated motion is a type of variable motion in which the velocity of a body changes at the same rate throughout the motion. The car in the figure shows this type of motion. At time 0 second, the car is initially at rest, accelerates to 5 meters per second 1 second later, 10 meters per second in 2 seconds and 15 meters per second in 3 seconds. We see that the velocity of the car is increasing at a constant rate of 5 meters per second in each second, therefore its acceleration is 5 meters per second squared. Furthermore, uniform acceleration means that the average acceleration between any time intervals is constant. This average acceleration is also the instantaneous acceleration at any time. To begin with the anatomy of equations for uniformly accelerated motion, let us consider again a car in which, initially at time t sub I which is 0, it has an initial position x sub I from the stop sign as origin and moving towards positive x-axis at a velocity of v sub I. Then the car speeds up with constant acceleration a. At later time t sub f, its position is at x sub f with a final velocity of v sub f. Now this is where the story begins. Let us wrap up the three basic equations first. We recall that the average velocity is equal to the change in position delta x over time interval delta t. Then the average acceleration is equal to the change in velocity delta v divided by the delta t. We can also express average velocity as half of the sum of the initial and final velocities, which is applicable only for uniformly accelerated motion. We transform these equations by allowing t sub I equals 0 and t sub f be the time interval t, which means the time t is any later time from 0 second. We also change the average acceleration to instantaneous since the acceleration is constant. So this is the transformed basic equations and we mark them as equations A, B and C, respectively. Now from these three basic equations, we will derive 5 specific equations to be used in dealing with motion with constant acceleration. From equation B, final velocity v sub f can be expressed as the initial velocity v sub I plus the product of acceleration a and time t. So this is the first specific equation. Now for the second equation, we combine equations A and C. So the displacement x sub f minus x sub I is equal to half of the sum of the initial velocity v sub I and final velocity v sub f multiplied by time t. So this is the second equation. This equation is useful especially when solving final position x sub f with known final velocity at any later time, even if we do not know the value of acceleration. For the third equation, with known value of acceleration and without knowing the value of final velocity, we combine equations 1 and 2, so the final position x sub f can be expressed as the sum of the initial position, the product of initial velocity and time, and half of the product of acceleration and square of time. Likewise, in terms of final velocity and without requiring the value of initial velocity, so from equation 1, we solve v sub I as final velocity minus acceleration multiplied by time. Then combining to equation 2 gives another expression for final position x sub f as x sub I plus v sub f minus 1/2 a t squared. And this is the fourth equation. Lastly, for the fifth equation, if we solve for time t from equation 1 and substituting to equation 2, we can have derived the expression v sub f squared equals v sub I squared plus 2a multiplied by x sub f minus x sub I. This equation is useful especially when dealing with problems wherein time t is not given. So remember these 5 equations. We will use these equations frequently, so as much as possible memorize them. Of course, before using these equations in a particular problem, the first thing you need to do is to analyze carefully the problem. Properly identify given information and quantities to be solved, then select the most appropriate and simplest formula that will give the shortest solution as possible. It is also suggested to consider the following. Set the initial velocity to 0 if the body is initially at rest. Set the final velocity to 0 if the body stops moving. Acceleration is constant at any time t, but the final velocity varies with time. Let the initial position x sub I be 0 unless otherwise specified in the problem. If the velocity is constant, that is v sub I is equal to v sub f, you can set acceleration to 0, then the 5 equations are reduced to displacement equal the product of constant velocity v and time t. Now, to have a different view on this, let us investigate how these equations mean to our motional graphs. Consider a velocity time graph of a body, moving initially at a velocity v sub I, then accelerates at a constant rate a, which is represented by the slope of this line. At later time the velocity has changed by this height at. It is clear seen from this graph that if we add v sub I and at, the result will be the final velocity v sub f, which agrees with equation 1. In addition, the area under this line represents the displacement delta x of the body at later time t. Now from geometry we see a trapezoidal area which can be divided into a rectangle and a right triangle. We knew from geometry that the area of a rectangle is base multiplied by its height, so the area of this rectangle is v sub I multiplied by later time t. While for this triangle, in which the area is 1/2 base time height, has an area of 1/2 a times t squared. Adding these two areas will be the body's displacement delta x. Surprisingly, this agrees with equation 3. Now let us use these equations in solving problems. Problem number 8. A jet lands on an aircraft carrier at a speed of 140 miles per hour, approximately 63 meters per second. Letter A. What is its acceleration, assumed constant, if it stops in 2 seconds due to an arresting cable that snags the jet and brings it to a stop? Letter B. If the jet touches down at position x sub I equals 0, what is its final position? Letter C. If the overall length of the aircraft carrier 100 meters, do you think the jet landed safely? So establishing given information, here we have the initial velocity of the jet, which is 63 meters per second. At time 2 seconds, the jet has stopped, so set final velocity to 0. X sub I is also 0 according to problem statement. And the length of the aircraft is 100 meters. So the problem requires to solve for the acceleration of the jet, its final position, and we are going to verify. Before we solve this, make sure you have a copy, maybe on a piece of paper, the 5 equations we derived earlier. This will serve as quick reference. So for letter A, based on the given information, to solve for acceleration, we can use equation 1, that is v sub f equals v sub I plus a times t. Then we will do some algebraic transformation so we can solve for the acceleration. If you do that, acceleration will be the quantity of v sub f minus v sub I divided by the time interval t. Substituting values, 0 minus 63 divided by 2 will give an acceleration of negative 31.5 meters per second squared. Letter B, we select equation 2 in solving the final position x sub f. From this equation, we can eliminate x sub I and v sub f since their values are zeros. Always remember we can eliminate immediately from the equation those with 0 values. This is to make our equation simpler. Then substituting the given values. 1/2 of 63 times 2 will give jet's final position of 63 meters. By the way, you can also use equation 3 to solve for x sub f, but make sure you have answered acceleration in part A correctly. Letter C, to verify if the jet landed safely, we just compare the final position of the jet and the length of the aircraft carrier. Since the final position of jet, that is 63 meters, is less than 100-meter length of aircraft carrier, therefore the jet landed safely. Good thing there is a resting cable that serve as added braking system. Now here's another exercise problem exclusive for a bright student like you. Good luck. Exercise number 4. A car moves with an initial velocity of 15 meters per second, accelerates at a constant rate of 4 meters per second squared. Letter A, how much time it takes to travel 200 meters. Letter B, what is its velocity after this time? Congratulations for answering exercise number 4. I'm pretty sure you got them all. Now, let us give another example. This problem deals with two objects, one is moving at constant velocity and the other is accelerating at constant rate. Problem number 9. A car traveling at constant speed of 45 meters per second passes a trooper on a motorcycle hidden behind a billboard. 1 second after the speeding car passes the billboard, the trooper sets out from the billboard to catch the car, accelerating at a constant rate of 3 meters per second squared. How long does it take the trooper to overtake the car? We list down given information. The constant velocity of the car is 45 meters per second. We set the initial position of the trooper x sub I to 0. The initial velocity of the trooper is 0. And 1 second later after the car passes the billboard, the trooper accelerates at 3 meters per second squared. What we are going to solve is the time for the trooper to overtake the car. Let's begin the solution. So in order for the trooper to overtake the car, its position must be equal to the position of the car at later time t the trooper started to move from rest. Mathematically, the final position x sub f of the trooper equal x sub f of the car. Later, we will go back to this expression. Since the trooper is accelerating at constant rate, we use equation 3 for the position of trooper at later time t, x sub f equals x sub I plus v sub I t plus 1/2 a t squared. We can eliminate x sub I and vit, since xi is 0 and v sub I is also 0. So the equation becomes only 1/2 a t squared. Since the trooper has just started moving 1 second later after the car passes the billboard, it means that the car has already traveled 45 meters per second time 1 second, that is 45 meters. Afterwards the trooper started to move and will overtake the car at later time t. So there is an additional length of 45 meters per second times this later time t traveled by the car before overtaken by the trooper. With these, the final position of car x sub f is 45 plus 45 t. Now we have established expressions for their positions which we knew they should be equal, therefore we can equate them. So we have the expression 1/2 a t squared equals 45 plus 45 t. Substitute known information and try to rearrange because it appears that this is an expression of quadratic equation, so we transform this to standard form and omitting the units for a while for simplicity. This will give 1.5 t squared minus 45 t minus 45 equals 0. Finally solving for using quadratic formula, t equals the quantity negative b plus or minus the square root of the quantity b squared minus 4ac all over 2a. Substituting, the coefficient a is 1.5, b is negative 45 and c is also negative 45. Then using the plus operation will give a time of 31 seconds. That's it, it took 31 seconds for the trooper to overtake the car. So next time you drive your car, avoid overspeeding because perhaps somebody may catch you. Always obey traffic rules and policies. Now let us conclude what we have discussed about uniformly accelerated motion by considering this sample problem. Problem number 10. The performance of new model car is being tested as it moves straight along a horizontal ground. The car, initially at rest, accelerates to 10 meters per second for 3 seconds. It moves at constant velocity for 5 seconds and accelerates at a constant rate of 6 meters per second squared for 6 seconds. It moves again at a constant speed for 1 minute or 60 seconds. Then it comes to rest for 10 seconds. Letter A. Find the total distance traveled for the entire trip. Letter B. What is the average speed for the whole journey? Letter C. What is the maximum velocity attained by the car? Letter D. Draw the velocity time graph for the whole journey, and verify your answer in part A using this graph. This problem is quite long because we are required to solve for the total distance traveled, the average speed, the maximum velocity, and to construct a velocity time graph. For letter A, the total distance traveled. The figure shows the type motion happening in each time interval. We also indicate the known values of velocities, time and acceleration. Since the car is moving along a straight line, therefore the total distance traveled d is the same as the magnitude of the car's displacement delta x. By knowing the initial and final velocities at each type of motion, we solve for the distance traveled delta x sub a, delta x sub c and delta x sub b, using the equation delta x is equal to 1/2 of the quantity initial velocity plus final velocity multiplied by time t. For delta x sub b and delta x sub d, we use delta x equals vt, since they involved constant velocity motion. For delta x sub a, we see that the initial and final velocities are 0 and 10 meters per second, respectively. The distance traveled for the first 3 seconds will be 1/2 of 10 multiplied by 3. So delta x sub a is 15 meters. For delta x sub b, this involved constant velocity. Delta x sub b is vt, that is 10 meters per second times 5 seconds. So the second distance is 50 meters. Let's keep up. For delta x sub c, we solve first for the final velocity v using the equation, v sub f equals v sub I plus a time t. Substitute the values, 10 plus 6 times 6. So the final velocity will be 46 meters per second. Then using the displacement formula and substituting the values, 1/2 of the quantities 10 plus 46 times 6, will give a distance or displacement x sub c of 168 meters. Can you still follow? You may pause a while or you may rewind my explanation. Now for delta x sub d. It involves again constant velocity motion. So it is also v times t, 46 times 60. Therefore, delta xt is 2760 meters. Lastly, for delta x sub b, we have already initial and final velocities, 46 and 0, so no problem at all. Delta x is equal to 1/2 of 46 times 10. So delta x sub b is 230 meters. After solving the individual distances traveled for each type of motion, now we're ready to solve for the total distance by simply adding all of these distances from delta x sub a to delta x sub b. Therefore, the total distance traveled by the car is 3,223 meters. For average speed, we simply use the formula speed s equals distance d over time interval. We have already solved the distance to be 3,223 meters. For the total time interval delta t, we just had all of these indicated periods of time, so it is 84 seconds. Therefore, the car's average speed is 3,223 meters divided by 84, 38.4 meters per second. For maximum velocity v sub max, by observing our solution in part A, we see a maximum velocity of 46 meters per second. Although the car has attained a maximum velocity of 46 meters per second, its average speed is only 38.4 meters per second. Take note that maximum velocity is instantaneous velocity in nature. Now, for the last item on the required list, the velocity time graph. The first thing you need to do is to check the value of velocity at each indicate time. So at 0 second, the velocity is 0. 3 seconds later, the velocity becomes 10 meters per second. Plus 5 seconds later, so 8 seconds later, the velocity is still 10 meters per second. Plus 6 seconds later, so 14 seconds later, its velocity is 46 meters per second. Then at additional time of 60 seconds, therefore 74 seconds later, the velocity is still constant to 46 meters per second. Lastly, a 10-second additional time, or 84 seconds late, the cars has stopped, so the velocity is 0. After checking these velocities, I guess we're all set to construct the velocity time graph. I conveniently use 10-second increment for the time line as well as for the velocity line. Now we plot the points, use the values of velocity and time. First point will be 0 and 0. Then 3 and 10. 8 and 10. 14 and 46. 74 to 46 and 84 to 0. Then we connect these points using straight line. And this is how the velocity time graph for the car looks like. Now using the velocity time graph, we can determine the displacement or total distance traveled by the car. The area under the graph represent the displacement, or total distance, traveled by the car. We see that each displacement has a shape, either a triangle, rectangle or trapezoid, and applying the formula of geometric area of these shapes will give a total area of 3,223 meters. This triangle area is actually the delta x sub a, which is the 1/2 3 times 10. This rectangle area is delta x sub b, that is 5 times 10 from this expression. This trapezoidal shape represents delta x sub c, which is the 1/2 times 6 multiplied by the sum of 10 and 46. This large rectangle is the delta x sub d, which is, from the equation, the 60 times 46. And lastly, delta x sub e is represented by this triangle, and the area is 1/2 of 10 times 46. The total area of this shape represents the car's displacement for the 84-second journey. As expected, this value is the same as our answer in part A. Now let us again check your understanding by answering the following exercise. Exercise number 5. The velocity time graph, shown in the figure, of a robotic rover is being plotted in a laboratory as it moves along a straight path for a period of 30 seconds. Letter A. In what time intervals the robot is accelerating and decelerating? Letter B. Determine the average acceleration in time intervals 10 to 12 seconds, 22 to 24 seconds, and 28 to 30 seconds. Letter C. In what time intervals the rover is moving at constant velocity? Letter D. What is the rover's average speed and average velocity for the entire 30-second period? Hint. Solve for the area above and below the timeline. Total distance traveled is equal to the sum of these two areas, while total displacement is also equal to the sum, but the area below the timeline should be a negative value.